Addressing stray voltage in a pool environment requires a systematic approach to identify and eliminate the source of the voltage. One key observation is that the stray voltage disappears when the bond wire to the pool pump is removed, suggesting the pump or its wiring is a likely source of the problem. It's important to never swim if there is stray voltage. Loose or damaged grounding connections can introduce stray voltage, so verify all grounding connections at the pool equipment, electrical panel, and any other relevant locations. Ungrounded electrical equipment in the pool area, including lights, pumps, and filters, can also be a source. Ensure everything is properly grounded. Improper pool bonding can also be a factor. The pool should be bonded to the grounding system to equalize any potential differences. Check the pool bonding wire and ensure it is intact and connected correctly. Faulty electrical wiring, such as damage, loose connections, or shorts, could cause voltage leaks. Similarly, a faulty pump motor or other electrical component can cause voltage leaks. Test the pump and other equipment with a voltage meter. Corrosion or rust on grounding connections or other metal components can lead to increased resistance and voltage leaks. Elevated groundwater can create a path for stray voltage to reach the pool. Check for any signs of elevated water levels near the pool. To solve stray voltage, first isolate the problem. Remove the bond wire to the pool pump and measure the voltage. If it disappears, the issue is likely related to the pump or its wiring. Next, check all grounding connections at the pool equipment, electrical panel, and other relevant locations. Tighten any loose connections and replace any damaged wires. Then test the electrical equipment, including the pump and other components, with a voltage meter. Replace any faulty devices. Ensure that the pool is properly bonded to the grounding system. Inspect the bonding wire for damage or corrosion. Trace the electrical wiring from the pump and other equipment to the electrical panel. Look for any signs of damage or loose connections. If these steps do not resolve the issue, consider a ground isolation transformer. This device can isolate the pool equipment from the main electrical system and help prevent stray voltage. If unable to resolve the stray voltage issue, contact a qualified electrician for assistance. Understanding grounding and bonding is crucial for electrical safety, particularly in environments like swimming pools where water and electricity create potential hazards. Grounding provides a path for fault current to return to the source, tripping a breaker or fuse and disconnecting the circuit, while bonding connects metallic parts to equalize potential and prevent voltage differences. The National Electrical Code, or NEC, provides specific requirements for grounding and bonding in swimming pool installations to minimize the risk of electric shock. Here are some key concepts and practices related to grounding and bonding. Grounding refers to connecting electrical equipment and systems to the earth, providing a low impedance path for fault currents. The main purpose of grounding is to protect people from electrical shock and prevent damage to equipment. The grounding system typically consists of a grounding electrode, such as a ground rod or ground plate, connected to the electrical panel via a grounding electrode conductor. Equipment grounding conductors, or EGs, are run with the circuit conductors to provide a path for fault current back to the source. Bonding involves connecting all metallic parts in and around a swimming pool to create an equipotential plane. This includes the pool reinforcing steel, metal fittings, pump housings, and any other conductive elements. The purpose of bonding is to minimize voltage differences between these metallic parts, reducing the risk of electric shock if someone touches two different parts simultaneously. Bonding is typically accomplished using solid copper bonding conductors, which are connected to each metallic part with listed bonding connectors. The NEC specifies the size and installation requirements for bonding conductors. The NEC Article 680 covers the requirements for swimming pools, spas, and hot tubs. It provides detailed guidance on grounding, bonding, wiring methods, and equipment installation to ensure electrical safety. Some key requirements include bonding all metallic parts within 5 feet of the pool, using insulated copper conductors for bonding, and installing ground fault circuit interrupters, or GFCIs, for receptacles and equipment serving the pool. When dealing with stray voltage issues, a systematic approach is essential. Firstly, inspect all grounding and bonding connections. Check for loose, corroded, or damaged connections and tighten or replace them as needed. Use a multimeter to verify the continuity of the grounding and bonding system. Secondly, test the voltage between various points around the pool. Measure the voltage between the pool water and the surrounding ground, as well as between different metallic parts. If you find any significant voltage differences, investigate the source of the voltage. Thirdly, isolate the problem. Disconnect electrical equipment one at a time to see if the voltage disappears. This can help you identify the faulty equipment or circuit. Fourthly, consider using a ground isolation transformer. This device isolates the pool equipment from the main electrical system, reducing the risk of stray voltage. Fifthly, ensure that all electrical equipment is properly listed and labeled for use in swimming pool environments. Use only equipment that is designed for wet locations. Sixthly, install ground fault circuit interrupters, or GFCIs, for all receptacles and equipment serving the pool. GFCIs are designed to detect small ground faults and quickly disconnect the circuit, protecting people from electric shock. Troubleshooting stray voltage in a pool requires a systematic approach and careful attention to detail. Understanding the principles of grounding and bonding, following the NEC requirements, and using appropriate testing methods are essential for ensuring electrical safety. If you are not comfortable working with electricity, it is always best to consult a qualified electrician. Stray voltage, also known as neutral to earth voltage or tingle voltage, refers to the presence of a small voltage potential between the grounded neutral conductor and the earth or other grounded objects. While typically low, this voltage can sometimes be felt as a mild shock or tingle, and in certain circumstances, it can pose a safety hazard. Stray voltage can occur in various electrical systems, including residential, commercial, and industrial settings. Several factors can contribute to the presence of stray voltage. One common cause is imbalanced neutral currents. In a balanced three-phase system, the neutral conductor should carry little to no current. However, if the loads and the different phases are not equal, the neutral conductor will carry a current which can create a voltage drop along the conductor's impedance. This voltage drop can result in a voltage difference between the neutral and earth. Another cause of stray voltage is inductive coupling. Electrical conductors can act as antennas, picking up electromagnetic fields from nearby sources such as power lines, transformers, or electrical equipment. These electromagnetic fields can induce voltages in the conductors, which can then appear as stray voltage. Poor grounding practices can also contribute to stray voltage. If the grounding system is not properly installed or maintained, it can create a high impedance path for fault currents, which can lead to voltage drops and stray voltage. Corrosion, loose connections, and inadequate grounding electrodes can all impair the effectiveness of the grounding system. Utility-related issues can also be a source of stray voltage. Problems with the utilities distribution system, such as imbalanced loads, faulty equipment, or improper grounding, can result in stray voltage that propagates through the electrical grid. Animals can be more sensitive to stray voltage than humans. In agricultural settings, stray voltage can affect livestock, causing reduced milk production, decreased weight gain, and behavioral changes. There are several methods for detecting and measuring stray voltage. A multimeter can be used to measure the voltage between the grounded neutral conductor and the earth or other grounded objects. It is important to use a multimeter with a low voltage range and high impedance to accurately measure the small voltage potentials involved. A ground impedance tester can be used to measure the impedance of the grounding system. This test can help identify problems with the grounding electrode, grounding conductors, or connections. A clamp-on ammeter can be used to measure the current flowing in the grounding conductors. This can help identify imbalanced neutral currents or other sources of ground current. Addressing stray voltage requires a systematic approach to identify and eliminate the source of the voltage. Firstly, inspect the grounding system. Check for loose connections, corrosion, and damaged conductors. Ensure that the grounding electrode is properly installed and has a low impedance to earth. Secondly, balance the loads on the electrical system. Distribute the loads evenly across the different phases to minimize neutral currents. Thirdly, shield electrical conductors. Use shielded cables or conduit to reduce inductive coupling from nearby electromagnetic fields. Fourthly, install surge suppressors. Surge suppressors can help protect equipment from voltage transients and reduce the risk of stray voltage. Fifthly, use isolation transformers. Isolation transformers can isolate sensitive equipment from the electrical system, reducing the risk of stray voltage. Sixthly, work with the utility company. If you suspect that the stray voltage is originating from the utility's distribution system, contact the utility company to investigate and resolve the issue. Stray voltage can be a challenging problem to diagnose and resolve. It requires a thorough understanding of electrical systems, grounding practices, and troubleshooting techniques. If you are not comfortable working with electricity, it is always best to consult a qualified electrician or electrical engineer. One tool that can be helpful is the ground fault circuit interrupter, or GFCI. This is a safety device that is designed to protect people from electric shock. It works by monitoring the current flowing through a circuit and quickly disconnecting the power if it detects a ground fault. Ground faults occur when current leaks from a circuit to ground, for example, if a wire comes into contact with a metal enclosure. GFCIs are required by the NEC in many locations, including bathrooms, kitchens, and outdoor areas. They are particularly important in areas where water is present, as water can increase the risk of electric shock. GFCIs are designed to detect even small ground faults, as little as 5 mA, and trip the circuit within milliseconds. This can prevent serious injury or death. GFCIs are relatively inexpensive and easy to install. They can be installed in place of standard receptacles or circuit breakers. When installing a GFCI, it is important to follow the manufacturer's instructions carefully. GFCIs should be tested regularly to ensure that they are working properly. To test a GFCI, press the test button on the device. This should cause the GFCI to trip and disconnect the power. If the GFCI does not trip, it may be defective and should be replaced. Another important safety device is an arc fault circuit interrupter, or a SI. This is a type of circuit breaker that is designed to protect against arc faults. Arc faults are dangerous electrical faults that can cause fires. They occur when electricity jumps between two conductors, creating a high-temperature arc. Arc faults can be caused by damaged wiring, loose connections, or faulty appliances. SIs are designed to detect arc faults and quickly disconnect the circuit, preventing a fire. SIs are required by the NEC in many locations, including bedrooms, living rooms, and dining rooms. They are particularly important in areas where there are many electrical appliances and devices. SIs are more expensive than standard circuit breakers, but they provide an important layer of protection against electrical fires. When installing an SI, it is important to follow the manufacturer's instructions carefully. SIs should be tested regularly to ensure that they are working properly. To test an SI, press the test button on the device. This should cause the SI to trip and disconnect the power. If the SI does not trip, it may be defective and should be replaced. Proper wiring practices are essential for electrical safety. When wiring an electrical circuit, it is important to use the correct size wire for the load. The wire size is determined by the ampacity of the circuit, which is the amount of current that the wire can safely carry. If the wire is too small, it can overheat and cause a fire. It is also important to use the correct type of wire for the application. For example, an M cable or non-metallic sheet cable is commonly used for residential wiring. It consists of 2 or more insulated conductors wrapped in a plastic sheath. UF cable, or underground feeder cable, is designed for underground installations. It is moisture resistant and can be buried directly in the ground. When making electrical connections, it is important to use the correct type of connectors. Wire connectors, also known as wire nuts, are used to join 2 or more wires together. They should be sized correctly for the wire gauge and tightened securely. Electrical tape is used to insulate electrical connections. It should be applied in multiple layers to provide a good seal. When working with electricity, it is important to follow all safety precautions. Always turn off the power before working on any electrical circuit. Use insulated tools and wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not comfortable working with electricity, it is always best to consult a qualified electrician. This explanation can assist with understanding of stray voltage, grounding, bonding, and safe electrical practices. These practices are critical for safety and the prevention of electrical hazards.